So hi all, in this lecture we will check whether a given function is convex, concave or neither at the points of optima. But on the last section we will discuss about a function of a single variable x, but on this lecture what we will focus on a function of a multiple variable, and we will check whether it is convex, concave or neither at the points of optima. So here we give a function called f of v. We are going to find out whether this f of v is concave, convex or neither. And here this f of v stands for vector which is consisting of two variables x1 and x2. Since it is multiple variables function, we are going to deal with two variables, that is x1 and x2. So in order to locate the stationary points, first step is we are to find the single order partial derivatives with respect to x1 and x2. That is, we need to find out the single order partial derivative with respect to x1 and single order partial derivatives with respect to x2. So this is here v is equivalent to this function, to x1 cube up to this much. This function is named as y. And so first we have to find out the single order partial derivative of f of v with respect to x1. So we can consider the each term. First we consider this term, and now here we are going to derivate it with respect to x1. So what really will happen, this 3 comes here, so 3 into 2 x1 raised to 2 by 3, and this 3 and this 3 got cancelled. So the final answer of this particular term is 2x1 square. Next we will consider 2x1 by x2 minus 2x1 by x2. So here we need to find the derivative with respect to x1. So we consider this x2 as a constant. So here we have two constant, 2x2, 2 and x2. So the derivative of 2x1 x2 with respect to x1 is 2x2. Now we consider this one, minus 5x1. So the derivative of 5x1 with respect to x1 is 5. And now we can have this 2x2 square. Actually these entire term is considered to be a constant. So the derivative of a constant with respect to x1 is 0, or derivative of a constant is a 0. So here we get 0. Here also there is no x1 term, there is only x2 term. So it also, the answer will be 0 when it is derivative with respect to x1. Here 5 is a constant, so the derivative of a constant is 0. So the derivative of this function with respect to x1 is 2x1 square minus 2x2 minus 5. This is actually a basic single order partial derivative. If you are still doubt, you have to go through how to find a single order partial derivative. Next we derivative the same function with respect to x2. So first we consider this term, that is 2x1 cube by 3. So as I said you earlier, since there is no x2 components, we consider the whole term as constant, and the answer of this is 0. So we consider the next one. Fortunately there is an x2 term, so we need to differentiate it, and here the 2x1 and minus 2 is considered to be the constant. So the derivative of minus 2x1 x2 with respect to x2 is minus 2x1, and next is this minus 5x1. Since there is no x2 term, this and derivative of this term, particular term with respect to x2 is 0. So we discard that and we take this one. So when you consider this, we have to consider the simple also, plus 2x2. We have the derivative with respect to x2, so we will get 4x2, and next 5. Here the next we have 4x2 plus 4x2. This 4x2 is actually the derivative of 2x2 square. Next we have to derivate this 4x2 with respect to x2, and the answer will be 4. and 5 is a constant, so constant derivation of a constant is 0, so we exclude that. So we get the single order partial derivative of function with respect to x1 and with respect to x2. So after finding the single order derivative, we have to find the value of x1 and x2. For that we equate this derivative to 0, these two derivatives to 0, and we named it as equation number 1 and equation number 2. And in order to solve x1 and x2, first we multiply the equation number 1 into 2. That is like we can use any method to solve a quadratic equation. The method I used here I will explain now. So if you have any other techniques to find the value of x1 and x2, you can go ahead with that. So here what I do is first I multiply this equation number 1 to 2, then we obtain this quadratic equation and we numbered it as equation number 3, and then we sum this equation number 3, that is this one is added to equation number 2, that is minus 2x1 plus 4x2 plus 4, and here this 4x1 square remains the same, minus 2x1 remains the same, but this minus 4x2 and plus 4x2 got cancelled, and minus 10 plus 4 we get minus 6 is equal to 0. So we get a final equation like this, and using this equation we need to find out the value of x1. For the both these equations there is two variables x1 and x2, so we perform all these steps in order to make this quadratic equation having a single variable. So using this equation, that is quadratic equation formula minus b plus or minus root of minus b square minus 4ac by 2a, we are going to find out the value of x1. So while solving we get x1 as equal to minus 1 3 by 2, and we substitute this x1 value to any of the two equations, that is 1 or 2, in order to find out the value of x2. So in that case, if you put the value of x1 in the equation number 1, we will get, when x1 is equal to minus 1, we will get x2 equal to minus 3 by 2, and when x1 is equal to 3 by 2, we will get x2 is equal to minus 1 by 4. Since I explained you earlier, like we are using a vector formula which is consisting of x1 and x2. So when x1 is equal to minus 1, x2 is equal to minus 3 by 2. When x1 is equal to 3 by 2, x1 is equal to minus 1 by 4. So this is the method we locate the stationary points. Now we got the two stationary points, that's on vector format v1 and v2. And next the third step is to construct an Hessian matrix. So what is an Hessian matrix? Hessian matrix is a square matrix which is consisting of the second order partial derivative. Consider this as an Hessian matrix. We have two variables x1 and x2 we represent here, and this is the second order partial derivative, dou square y by dou x1 square. This x1 square is nothing but x1 into x1. When you consider this particular term, dou square y by dou x1 x2, x1 into x2. So here is s2, denominator is dou x2 x1, that is nothing but x2 into x1. Here we get x2 square, that is x2 into x2. So here we construct the Hessian method. Next we are going to find out each term individually. That first we have to find out dou square y by dou x1 square. So basically from the equation 1 we have dou y by dou x1 is equal to 2x1 minus 2x2 minus 5. So we write that here 2x1 minus 2x2 minus 5, and we are going to differentiate these polynomial with respect to x1. So here is an x1 term, control. So we are going to differentiate this term with respect to x1, and we get 4x1, and these two terms, that minus 2x2 and minus 5 is constant, since we are going to derivate it with respect to x1. So we didn't consider this term. So the answer for dou square y by dou x1 square is equal to 4x1. And dou y by dou x2 is equal to minus 2x1 plus 4x2 plus 4. That is actually our equation number 2 that we derived our first order derivative in the first step itself. And we are going to differentiate it with respect to x2. So since this term is an x1 term, we can discard this term, and since it's an x2 term, we are going to differentiate this with respect to x2. So 4x2 differentiated with respect to x2 is 4. Since 4 is a constant, the constant derivative is 0. So we are going to exclude it that too. So now we get dou square y by dou x square. Next is dou square by dou x1 dou x2. So here we split this into like dou by dou x into dou y by dou x2. That is dou by dou x1, the first term. In bracket we consider dou y by dou x2, that's the second term. So the second term we consider here, and the first term we consider here. That is x1 we consider here, and x2 we consider here. So dou y by dou x2 is nothing but minus 2x1 plus 4x2 plus 4. So we will write here. So what we are going to do is we differentiate this particular polynomial with respect to x1. So here we have an x1 term. So we are going to here we have an x1 term, and we are going to differentiate it with respect to x1. Minus 2x1, the answer is minus 2, plus 4x2 and plus 4 is constant, because we are considering to derivate with respect to x1. Similar scenario here dou square y by dou x2 dou y. So dou by dou x2 comes first, and dou y by dou x1 comes next. So this second term comes here. So here dou y by dou x is 2x1 square minus 2x2 minus 5. 2x1 square minus 2x2 minus 5. So here we are going to derivate this with respect to x2. So this is the only x2 term. We are considering it with a simple sign is actually important, and minus 2x2, if you derivative it with respect to x2, we will get minus 2. So we get all the terms, and we are going to write all the terms of the corresponding positions. So we will get the Hessian matrix as 4x1 minus 2 and 4. And our next step is we are going to find out the determinant of lambda I minus h. Lambda I is nothing but I is a square matrix, and lambda I means lambda 0, 0 lambda minus our Hessian matrix 4x1 minus 2 4. So here we are going to implement a minus operation that I forgot to mention in this equation. So when you perform this lambda I minus h, what will we get? Lambda minus 4x1, 0 minus of minus 2 will become 2, 0 minus of minus 2 will become 2, and lambda minus 4. Next we are going to find out the determinant of two vectors. We have two vectors, one is on minus 1 and 3 by 2. So first we are going to substitute these values in this corresponding Hessian matrix. Here we have lambda minus 4x1 in this particular location, that is our x1 value is minus 1. That is here x1 is minus 1 and x2 is minus 3 by 2. Luckily there is no x2 terms is available in this determinant notation. So we are just focusing on this x1 value, that is minus 1. So lambda minus 4 into minus 1. What will we get? Lambda plus 4. This minus into minus becomes plus. Plus 4. So we substitute the value here, lambda plus 4 to lambda minus 4. Now we are going to find out the determinant. Determinant is same as like lambda 4 into lambda minus 4 minus 2 into 2. That is the way we find out the determinant. We cross multiply the determinant if it is in a square matrix. So lambda 4 into lambda minus 4 minus 2 into 2. 2 into 2 is 4. So lambda plus 4 into lambda minus 4 is in the format of a plus b into a minus b. So a plus b into a minus b is a square minus b square. That is lambda square minus 4 square is 16, and here this minus 4. So basically we will get lambda square minus 20. So there we find out the determinant of a particular matrix, square matrix. But the real agenda of finding out the determinant is we have to find out the value of lambda. So next step is to find out the value of lambda. So based on the value of lambda, we are going to check whether it is convex, concave or neither. So for that we equate it into 0. So we get lambda square is equal to 20. So lambda is equal to plus or minus root of 20. So actually we are not concerned about the value. We are really concerned about the sign. That is like, this is the rule to find out convexity and concave of a function when we deal with the multiple variable. That is, if the eigenvalues are positive or some are negative or some are 0, then the function is neither strictly concave or convex. That is, in the current scenario what we get is we get plus 20 and minus 20. So we get one value as positive and one value as negative. So we can say like at the point minus 1 3/2 it is neither strictly concave or neither strictly convex, or neither at the point of optima. And next we consider the second point, that is V2, 3/2 minus 4 minus 1/4. The same scenario is same method is same as the earlier one. We are going to substitute the x1 value, that is 3/2 value. Here we will get lambda minus 6, and we equate that value in the Asian matrix. So lambda minus 6 2 to lambda minus 4, and then we are going to find out the determinant, lambda minus 6 into lambda minus 3. Here we use a lambda minus 6 into lambda minus 4. So we get, by solving this equation, we get lambda square minus 10 lambda plus 20. X minus a into x minus b is equal to x square minus a plus b into x plus a into b. That is the equation used here. Minus 4 equal to 0. And by solving this, we will get an equation like this. And when you find out the lambda 1, we get 5 plus root 5, and lambda 2 is equal to 5 minus root 5. So we get two values, but both the values are positive. Even though it is negative 5 minus root 5, we will get a positive value. So we can tell like this, it is a strictly convex. So by conclude, in order to determine the convexity of a multivariable function, we find out the Hessian matrix and we solve to find out the value of lambda. Depending upon the value of lambda, we will check whether it is convex, concave or neither. If all the values are positive, then it is convex. If all the values are negative, then it is concave. And if it is convex, we can say it as minimum. If it is concave, we can say it as maximum. And if the some values are positive, some values are negative, then we can say it as neither strictly concave or strictly convex. And if some values are positive, that is if 0, that is if you will get a positive value and a 0 value, on that condition also we can go for the neither case. So I hope you understand how to check whether a function is convex, concave or neither in the condition of multivariable function. Thank you all.